Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm here to talk to you about a new system that my group has been building over the last year or so. It's a system called HyperDex, and it's a key value store. And so, unless you've been hiding under a rock, I think you must have noticed the big transformation in the data storage space over the last 10 years. So for approximately 30 years, we had the same single architecture for all databases, which was a single centralized server with a huge collection of disks. And that database supported a very nice interface, a SQL interface, and provided some very well-defined features known as ACID. And what happened in the last 10 years is that people realized that that architecture was unable to scale up and did not meet their performance demands, and therefore they came up with an alternative scheme called NoSQL. And so these NoSQL systems essentially work by sharding the data across a cluster of machines. And starting with Dynamo and systems derived from Dynamo, they all happen to have the same distributed architecture. And that architecture ends up having three fundamental problems just as an inherent part of what it is. And those three problems are that of search, secondly of consistency, and of fault tolerance. The specifics are going to vary between systems, but if you look at systems like Mongo, React, Cassandra, and so forth, these systems, Voldemort and so forth, these systems that you have heard about and systems that people are deploying left and right, they tend to suffer from these three problems. Now, before I describe the three problems in a bit more detail, if you look at these systems, the core architecture is very simple. They use consistent hashing. They take a key for each object. They hash the key to a particular location on something like a ring. And then the object is located on the host that the key maps to. Now, this is fine. The problem, of course, is when it's time to do a search. And I'm looking for, let's say, I've keyed everybody by their user ID, and now I would like to find everybody located in Seattle. That's a very difficult search because these objects would have been spread out, smeared across my entire cluster, and I need to contact every single person. The second problem, of course, has to do with consistency. It's generally very difficult to achieve consistency in a distributed system, especially in these kinds of systems. One can have situations where different clients disagree on the state of the network. So even on a good day, when you're adding new nodes to your cluster, you can get into situations where people are trying to perform updates, and they end up performing their updates on disjoint sets. And even when they purportedly use quorums, because they're not actually agreeing on the membership of those quorums, these systems tend to have consistency problems. And the third, and again, one of the major problems with this approach is fault tolerance. So these systems, in any kind of a distributed system, you will end up having failures, and to cope with failures, you will have to replicate the data. A lot of these existing systems consider a write complete even before it's been spread out to all replicas. So I don't have time to describe for you the entire system, but I want to just give you an intuition for the architecture of our system, and I want to just drive home one message, which is a message of hope. So first, let me describe to you what it is that we've built. We built this system called HyperDex. It has some features not found in any other NoSQL store. It is consistent, it is fault tolerant, and I can expand this fault tolerant into it's available, it's partition tolerant. So you've heard of the CAP theorem. I just mentioned something that should probably raise some heckles here. It's also high performance, it achieves high performance, it's scalable, it's got a rich API. Let me be, just before you run me out of town, just at this point, I am not claiming to have violated the CAP theorem. The CAP theorem is what it is. But there's a key phrase here, a threshold of failures, that allows us to circumvent the difficulties imposed on us by the CAP theorem. So let me just give you the architecture of our system very briefly. It's very, very simple. We don't do that consistent hashing trick. We do a different kind of a hashing trick. It's called hyperspace hashing. And imagine that I have a very simple data store with multi-attribute objects. Normally, I would take these objects and I would hash, let's say, S session, and it would give me some number 17. It would determine exactly where my object is. Instead, I determine a different coordinate for this Srini object. I hash Srini separately, I hash Seshan separately, and I then go to the phone number location. I have a 3-tuple in my hand that corresponds to a coordinate for the Srini object. Then, so in this case, Neil Armstrong maps to that location. Let's see, if I had Lance Armstrong would hash to a different location. Lance would, of course, lie on the same plane on the first name. This is Lance. Is that right? I don't know which one's which. Anyway, so in any case, it's hard to find out what exactly they are at the moment. But let me actually have a bet. What happened? Okay. Okay. So all right. So these objects each have a coordinate assigned by their attributes. We then take the space, we chop it into different blocks, tessellate the space, assign it to servers, and so that way, if I had to do a search for, let's say, all the Neils in this world, they would end up lying on this plane. And if I had to do a search for all the Armstrongs, they would have to lie on this other plane. And I only need to contact half the nodes in my cluster of 8 nodes here. And if I had to search for, say, I don't know which one this is. Again, this is Neil Armstrong or something of that kind. I'd have to do a search that involves only 2 hosts. And I can also very easily do range searches in this universe because, again, there's a very easy mapping. So this is the core idea behind hyperspace hashing. There are a couple of other ideas that I don't have time to go into involving how to replicate in a consistent manner. And the upshot of that approach gives us a system that has consistent updates to replicated data in a sharded data store. Let me just say a few words about the CAP theorem, which, so most of you know the CAP theorem with its sexy, catchy title, which is consistency, availability, partition, tolerance, pick any 2. So that's a very nice way of phrasing things. In fact, there are salesmen going around Silicon Valley educating, if you will, the developers in what the CAP theorem says, and just instilling in them this dreaded fear that you can never have these 3 properties in any shape or form, and therefore you must give something up. It's kind of like Lent. And as a result, what they say is, well, look, you can't have all these 3 things. We have this store. It does A and P. We don't do C. So they sell these highly inconsistent data stores, and a lot of our critical infrastructure is now moving off of good old ACID databases towards NoSQL stores with very, very weak properties. Let me just tell you a little bit about what the CAP theorem really says. It's a very, very simple theorem. What it says is, if you cannot limit the number of faults, if you want to assume, if you have to live in a universe where anything can fail, including any network link, including every network link, and by availability, every single one of your servers has to respond to every query that's incident upon it. And because everything can fail, they can't communicate. Well, then they cannot be consistent. So that C conflicts with that A under the presence of P. It's a very simple tautology. There is no deep insight here. So it's very easy to work around as a result. What you can do is you can say, well, look, if I know that my failures can be somewhat constrained, if I have designed my data center such that it will tolerate, the probability of a catastrophic failure involving more than F nodes is somewhat small. There are professionals who can do this kind of thing. Then I can actually make some progress. So that's exactly what we do. And I think I want to just end on that note without taking any more time. So if you have questions, this is a very large project. More people outside Cornell have contributed code to it than people inside Cornell. It's open source, and everything's on the website.
Do you have Q&A?
Yeah, Atul.
So how do you compare this? How do you classify Bigtable and Spanner?
Bigtable, those are great.
How does this compare to them?
So Bigtable and Spanner are Paxos-based, so they provide consistency guarantees.
Do you classify them as NoSQL or SQL? They don't have a SQL interface.
I don't know what NoSQL is. Right? I've never seen a software movement as proud of its lack of features as NoSQL. So it is Spanner and Bigtable and so forth are what they are. Column-oriented storage systems. They're all in the same amorphous sort of bin. So I didn't talk about our transaction management system. We do not use Paxos. And I would consider Spanner and Scatter to be heavyweight systems that apply the Paxos hammer to an issue which does not require the Paxos hammer. So Yeah.
Just a clarifying question. You said that a bunch of NoSQL systems fail if you ask for a query on which the key is not partitioned. And then you had tested the data along multiple keys, right? So in your example, if I was looking for people who landed on Moon,
okay,
you would have the same problem. You would have to go search across all the servers, yes?
Sure, that is.
Not, I mean.
So what you're saying is if I just make up attributes on the fly,
yeah,
then it becomes
or an attribute on which you didn't happen to test it.
This is a system for attribute-oriented data. So this is not for a blob store. It's not for random queries that come up out of the blue. We've actually built systems for that kind of thing. We built something called Qubit that actually gets at what you're doing. This is not it. This particular trick works for multi-attribute data.
Okay, thank you.
Great, thanks.
So the question that was posed to us was what we think is an important problem for industry to focus on, and basically why should the industry care or not care about a particular research topic. And I'm going to talk about transport issues in data centers because that's something I've sort of thought about for a while. But there's this larger point that I want to take this opportunity to make, and that's that well, I've been working at this SDN networking startup for about 7 months now. And from my vantage point, it seems to me that as an industry, at least that portion of the industry that's focused on data centers and cloud is sort of very much right now focused on software-defined networking and just trying to build like a better control plane and management plane for our data centers and the cloud. And the point that I want to make is I think the data center does need a lot of innovation in the data plane as well, and sort of the core kind of networking. And even if we don't maybe necessarily feel that today, my belief is that we will soon. So as we deal with the current challenges that we have in the control plane and the management plane, and as we move more and more applications in the cloud, we'll start hitting these performance bottlenecks that can really be addressed in the data plane. So that's the sort of main thing that I want to put out. But just to give you a sense of where I'm coming at this from, there's this vision that the data center is going to be this warehouse scale computer. So it's just going to be this collection of resources that we can pool and we can run sort of this one infrastructure that's going to run all of our applications. And for this vision to really materialize, we need to get to the point where running an application in the data center is as easy as running it on any other computer. It should just be very trivial. So that means we need to be able to spawn workloads anywhere. We need to do resource pooling. And maybe most importantly, we need to have this concept of agility where we can sort of provision an application on demand, scale it up, scale it down, tear it down, and do all these nice things. And today, we often hear that we're not really there yet. And even though we have virtualization technologies, we often hear that the network's in the way. And of course, SDN's going to come and save us all from this. It's going to give us all these nice L2, L3 virtual networks. We're going to be able to create them, scale them up, scale them down, move them, and do all these great things. But what about performance? So is the performance of the data center where it needs to be, where an application is as easy to run in the data center as it is to run on any computer? And what I would argue is that no, it's not so great right now, at least in some particular ways, at least in some aspects. And I'll give just 2 examples here, which are, I think, the most pressing today. One, in terms of latency performance of data centers, and second, in terms of performance isolation in a multi-tenant environment. So we have this shared infrastructure, we have all these different tenants. Can we actually isolate their performance from each other so that we can give some guarantees to the performance of the individual tenants? And the reason I say this is these problems are not going to let us sort of really get to that full vision because currently these problems really do limit what applications can do in a data center, and they make life hard for developers. So just as we said the network's in the way from the management and operations perspective, I think at some point we'll realize that the network is in the way from a performance perspective as well. So just some, I think maybe I'm preaching to the choir, but there's just some anecdotal evidence for this. we've seen all these studies of what happens when people move applications in the cloud. So Netflix has this nice blog entry that you can go and see, and it talks about their experience when they moved to AWS, and they sort of talk about how they basically had to restructure and think again about a lot of the way their applications were, a lot of the things that their applications were doing, especially in terms of how chatty their APIs were because of the performance variability that they saw in the cloud. So people are overhauling their apps to deal with this variability, and so it's not so simple to really move everything to the cloud. And of course, someone like Netflix, these are sophisticated, people. These are sophisticated customers. Most people won't even realize that they're having these network-related issues, and they'll sort of maybe just say, okay, well, I'm seeing this problem. I'm just spin up more VMs or do something like that. And what I want to stress is that these are really hard problems. You basically can have variability issues and these performance problems everywhere in the stack. So we kind of have to go after it everywhere. And there are lots of various activities in academia and some in industry to address these right now. So like, your software stack needs to be optimized. I/O, disk, NICs are big performance bottlenecks. Just network hardware itself and protocols, which is something that I've worked on a little bit. And again, I want to say that these are predominantly data plane problems. And the way I think of that is it's sort of a question of the time scales at which these problems manifest themselves. Most of these problems, they can sort of show up in sub-millisecond or millisecond time scales, and by then you have to be able to react. And if you can't react, then you've already have the problem. So SDN is not going to help us with these things much. I mean, there's maybe some ways we can think about sort of helping sort of configuring things and controlling things through SDN, but these problems are really data plane problems. And just as a very quick example of this, this was just a simple thing we did in the lab at Stanford to just demonstrate this. We have co-located VMs on a receiving machine, and you have this application that generates TCP traffic, and you have this other one, this other red VM that generates this bursty UDP traffic. So it doesn't send sort of at a necessarily high rate, but it's kind of bursty. It sends for 5 milliseconds, and then it's off for 15 milliseconds. And if you go and you look at like a network performance monitor for this, and you look at bandwidth, you see, well, the UDP guy is not really necessarily, it doesn't look like he's doing something really wrong. He's sending at less than 3 gigabits per second, but the TCP performance is pretty bad, and it's not able to grab a lot of bandwidth. And the problem with this is, of course, you're looking at sort of aggregates over about a second, and you don't really see this. So if you zoom into this, you see that you're causing these bursts on millisecond timescales, and that's already bad enough to cause these performance problems. So we have been working on a system. This is really the work of Vimal Jayakumar, who's a student at Stanford, and professors at Stanford, and Albert and Chang, who's actually here, have been collaborating on this. So I won't go into a lot of detail on this in the interest of time. I just want to sort of say what it does. Basically, it's a system that allows you to provide bandwidth guarantees to these virtual tenants in a multi-tenant environment. So just like today we can say, okay, from reachability and control plane perspective, we can have a tenant and it's completely isolated. We want to say from performance perspective, this tenant can be isolated. And just as you would go and you would when you're asking for these resources, you would say, I want this much memory, this much CPU, this much storage. We want to be able to say you want to specify sort of the thickness of the pipes that you get into the network and have that be guaranteed. And again, I want these guarantees to be at sort of millisecond timescales. And so all these mechanisms are in the data plane. I'll skip over the sort of architecture. I'll just show you just one illustration of what this thing can do. So this is an experiment. It's a Memcached sort of workload that gets interrupted by a bad behaving tenant. And you can see that the latency for these Memcached requests, if you don't do any isolation, it quickly shoots up, and it's pretty bad at the tail. And you can actually do a pretty good job of protecting it if you have these fast reactive mechanisms in the data plane. So with that, I'll again just reiterate my takeaway that we shouldn't be forgetting that in the midst of all this SDN stuff, we do need to innovate in the data plane of the data center as well. And That's it. Thank you.
This is a clarifying question. So you started and ended by saying we need to innovate in the data plane, and then you talked about performance isolation.
Yes.
Is there a distinction between the two in your thoughts?
So
is there anything else at the data plane? In other words, suppose you somehow magically solve all the performance isolation problems. Are you done? Or what's the?
Well, so for me, the two most glaring questions of like where we need to focus in the data plane are latency and performance isolation. These are two most obvious ones. But I think when we get down to actually solving those, we'll come to other ones. Like, for example, we need to be able to load balance, a data center well, and that's also a data plane problem. You need to do it at those time scales.
I think we have time for one more question. Hear me? All right, I'm Nathan Farrington. Title of my talk is called Copper's Dead. I'm a grad student at UC San Diego. Thanks for the introduction. So this is not original research of mine. This is a story that's well known in the optics and electrical engineering communities, but it's not well known in the computer science community. So what I'd like to do is just tell this story because we all need to hear this story. So receiver sensitivity. Like, let's say that I have a network adapter and I need to receive some power in order to differentiate between zeros and ones. I need to decode bits. What's the minimum amount of power I need to do that? So some adapters we had, the minimum power was 12.59 microwatts. So surely we must be able to get at least 12.59 microwatts of power to our receiver under all conditions, always. So why is there any problem? Problem comes because of attenuation. So if you have a communication channel, doesn't matter if it's wireless or wired or what technology, it's going to lose some power during transmission. So we put our minimum, 12.59 microwatts, on the other side. What's our input power? How much power do we need to put into the channel in order to get enough out of the channel to use that, to get bits? What's the attenuation of electrical cable? It is this equation up here, 7.2 times 10 to the negative 6 times the square root of the frequency of the signal. That's for electrical cable of a diameter of 3.6 millimeters, which is actually a fairly thick cable when you think about it. So that square root of f is the problem. So let's look at the different bit rates. At 1G, we're losing 15.3% of our power every meter. That's compounded. And as you go up to higher bit rates, 10G, that's 40% of the power is lost every meter. This is crazy, right? At 100G, it's 81% of the power is lost every meter. So you say, okay, well, theoretically, is there a maximum amount of input power? Can we just put enough power to overcome any type of loss in the cable? So fusion power. The amount of power required to melt a copper cable of a given thickness. So for this thickness, 561 watts will turn it to liquid. So you cannot actually, so theoretically, you cannot actually, there is a physical limit to how much data you can put through an electrical cable. Okay, so now that we have our max input and our minimum output, what's the maximum length of an electrical cable? We have our power budget, and we just divide. So for a 1 gigabit link, 106 meters. And 10 gig is 33 meters, all the way to 10 meters for 100 gigabits. You say, fine, I'm willing to, I can live with 100 gigabits at 10 meters. That's still pretty useful. But don't forget, these are for relatively thick cables and 500 watts of power per link. So this is crazy. Is there anything else we can do? Can we save the day somehow? Is there something in, yes, quick question.
I'm struck by the amount of minimum power you want at the receiver. That seems to be awfully high. I mean, a lot of wireless system operated at far lower power.
Minus 89 dB is your Wi-Fi.
So how did you get this?
Minus 19 dB? So you're saying minus 89 dB?
Is what the general is. And for the new receivers, minus 114 dBm.
I mean, NASA talks to...
This is good news. You're pushing the death of copper off into the future. It doesn't change the story, though.
Yeah.
Well...
Okay,
But is there anything else we can do? There's one more thing we can do. So capacity of a communication channel. Shannon-Hartley theorem. So this is, this is information theory. The capacity of a communication channel is directly proportional to the frequency of the signal. That's what we've been increasing. But there's another term, right? It's the log of the signal-to-noise ratio. What you want to do is you want to increase the frequency as much as you can first, because you get a linear increase in capacity. But then you want to increase the signal-to-noise ratio. You only want to do it second because you have a logarithmic penalty. Your return on investment for increasing the signal-to-noise ratio is really low. And that's the regime we're in right now. We're starting to invest all this technology into advanced codes for to do 10G. Even 1G has a lot of advanced coding to get 100 meters. And so this will not save the day. Logarithmic scaling is horrible in this case. So copper is dead. Yes, you can use more sensitive receivers, but you don't believe me.
No.
This is research, right? So it's copper maybe not dead today.
Copper could be dead for various reasons, but I don't believe that it's because of receiver sensitivity.
So do you think the receiver sensitivity can become as you can keep increasing the sensitivity of receivers forever? Or is there some limit to?
Well, it depends upon what the practical length of copper cables you want.
It has nothing to do with the length. I'm talking just about the receiver.
No, it has everything to do with the length. After a while, there is no point, for example, in having a copper cable that's longer than the diameter of the Earth. Okay? So there is no
we're not talking about Earth scale. We're talking about this length. This length is now untenable.
I think we already can, there are reasons to do fiber optics for all sorts of reasons.
I haven't even mentioned fiber yet.
So, fine.
All I'm saying is, it's like Karl Marx, he didn't write about communism, he actually wrote about why capitalism is bad. So it's kind of...
Right, so he also made lots of bad you know how that went, so.
So the receiver sensitivity cannot be infinitely small. At some point you have a single electron or a single photon. There's a physical limit there. Yes, you can push it off the death, but the death is coming. So let me just... Copper's dead. It really is. You can in the abstract I said you can kick and scream, but it's happening.
I am not denying the fact that copper is dead. I'm simply saying it's not dead because of what you were saying.
Hey, G2.
It's okay, fine.
Yeah.
Okay.
He's dead, man. He's dead.
It's not my research. I'm reporting on others' results. Okay, and I cite them. Okay, and so what is the attenuation of an optical cable? It is 2.0 times 10 to the negative 4 decibels per meter. It does not depend on the frequency of the signal. So two things we can conclude about optics. Very, very small loss for very high bit rates over very long distances. So how does this change how we think about building computer systems? Long distance computer systems, HPC interconnects, data centers, even in the home at high enough bit rates. That's why people build optical equipment, because of the physics behind it, not because they like optics or they're infatuated with the technology. It's just because of physics. Okay, so what's this mean for computer science? Computer scientists treat networking like the traditional concepts of packets and TCP and BGP convergence algorithms and all this stuff where you have mostly packets. You don't even think about the physical layer. You don't think about bits even. You only think about packets. But in a world where everything is optical anyway, what other knobs and levers does optics give us to build networks and computer systems that use those networks that we don't currently have because we're living in an electronic universe? So a lot of my research in grad school has been looking at how to apply optical technologies such as circuit switching in a data center environment where you do get huge wins because you're already optical. We're not saying you need to install this exotic technology. Exotic technology is there, we're just not using it. So what does this mean for computer science? It's an opportunity. There's multiple paths. In the future, we can either say, okay, optics, you are expensive links, which will get cheaper over time. And then we'll just do packets in the boxes. Give us you have the links, we have the boxes. Or we can say, let's do cross-layer optimization into, not just within computer science, but into electrical engineering and optics as well. So if any of you have been convinced, other than one person, that maybe there's a future in optics and computer science, and this might have some relevance to Microsoft, you can actually you can get in touch with university researchers, about 20+ professors, 100+ students, through this. I'm a member of this Center for Integrated Access Networks. It's the NSF ERC, and for in a structured interaction, you can access a very wide range of optics expertise. So you can actually have a conversation with them, if you want to collaborate on a project because you have some ideas, you want to learn more about optics. This is a great, this is actually something you can do. You can act on this. And so you don't have to just say, oh, I need to become an optics expert. No, you just...
What exactly are they doing? What is their mission? Charter?
Their charter is to improve access networks and data center networks with optical technologies. Question?
There's optical cables and then there's optical switching. These seem to be sometimes conflicted together, but they're very different beasts. Most of what you've talked about is optical cables.
I think the thesis is that if electrical cables are going to disappear and replaced with optical cables, then what other optical technologies can you attach to those optical cables anyway? Because if you're doing electronics in the boxes, you have to convert from optics to electronics and back again. You're missing some opportunities there. And you can put optics on chips. These researchers are building, systems on chips with optical doodads and widgets and things that the.
What do you think has happened in the last, this is 20 years old. A double DM concept was done 20, 25 years ago, and the problem was this whole, what you mentioned, electro-optical switches, which were gating the whole progress anyway. So has something interesting happened recently that is causing everybody to get excited again about this?
Data centers are an interesting thing that happened recently. HPC interconnects have been used for over 20 years. Long-distance communication has been used for over 20 years. You look at the state of research with in long-distance communications, optics papers, computer scientists don't accept optics papers at conferences. We think that this is something that EE should work on. And all this scheduling, wavelength scheduling over long distance, this is,
Telling me, you say data centers, I'm thinking of it okay, here's where you can use it, but what I was asking is, has there fundamentally been any change in any of the physics or even the, as I said, the electronics to optical switching?
These guys are so far ahead of us as far as all the different things that you can physically do with light, things that we don't even, can't comprehend. I only looked at optical switching because it's a commercial product, but they can do things with light and photons that you wouldn't classify as switching, or it's not just as simple as sending bits. There's some crazy stuff. There's also quantum computing or quantum communication that happens when you have optics. There's a lot of. What I'm saying is that this is the future, and this is a way to access part of the future and start laying the groundwork.
Thanks, Stefan. I found out that if you don't send in a title, Stefan selects one for you. So my title was listed as TBD, and I really spent at least as much time figuring out how I would make that work for my talk. And the rest of the talk, I'm afraid, has very little to do with the title. This is the best I could come up with. So what I'm really going to talk about today is how I think we're in a period of whether or not you believe in the whole theory of evolution, punctuated equilibrium when it comes to content delivery architectures. And I'm going to start out showing you one of my most famous favorite cartoon sequences. This is called A Short History of America by Crumb. And there's sort of the bucolic setting before, before the Europeans arrived. And This is actually even more fun if you sort of set it up as an animated sequence where you see one coming right after each other on top. But there's some notion of progress here. And I want to use this sort of as the backdrop for my discussion of the evolution of content delivery systems. And I'm only really going to try to make 3 interesting technical points in the whole talk. So if I come up with only 1 or 2, remind me, and I'll try to think of what the third one was. All right, so we started out with the client-server model. Okay, this was the way to get a website off the ground originally. This is sort of what we had. This model predates the web, but certainly, Tim Berners-Lee put together a web server and a web client, and the thing took off, became highly successful commercially. And the next thing we had was web hosting. Okay, so we had companies that would help you set up your website. We started to see data centers built. Today, the web hosting architecture has taken on a new twist. You can now have web hosting in the cloud, and lots of websites use, maybe not lots, but maybe lots of websites use things like Amazon Cloud Services. You hear about it like when they go down. So the web took off, and the next thing you know, a whole slew of companies were formed who were selling caching hardware. And these companies, many of them are gone now, but like Cashflow and Ink2Me, and also major hardware vendors who build other devices like Novell and Network Appliance and so on, started building caching hardware. And they kind of had a couple different applications. One that was fairly successful was called reverse proxy. Did I get that right? Where you put a whole bunch of caches in front of your hosting infrastructure just to give you better capacity there. That was a good idea. They also were hopeful that you could sell caches to ISPs who would then be able to put them in, throughout their networks and reduce the load of the centralized hosting infrastructure, and maybe also improve performance for the ISP's users. This was sort of contemporaneous with completely different paradigms like peer-to-peer content delivery, and we saw Napster and the evolution of these systems, and they're still very heavily used today. Like BitTorrent is sort of the canonical example of a successful peer-to-peer architecture. Most of this talk, though, I'm really going to be focusing on commercial content, where somebody is willing to pay to get their content out there. So we'll see how peer-to-peer is now kind of fitting into the commercial infrastructure, or the infrastructure that's supporting commercial content providers. But this has been there, peer-to-peer has been there for a long time, and it's still important today. And then we saw content delivery networks. And as Stefan said, I am from Akamai. I'm one of the people who started Akamai, and we weren't the first content delivery network company, though there were others before us, Sandpiper, Interview, and others. And this has developed into a big business today, on the order of at least a few $1 billion of revenue for companies like Akamai that deliver content on behalf of content providers. And I always like to come visit MSR, partly because Microsoft is Akamai's largest customer, and so we've had a strong partnership and are doing some very interesting things. Unfortunately, I've been told I'm not allowed to talk about some of the most interesting things, but I'll hint about them anyway. So the content delivery networks arose, and maybe in a bit of sort of irrational exuberance, different parties started to feel like, well, we're missing out on all this money. Okay, the CDNs are making tremendous amount of money, so we should do it too. And so other parties have decided they're going to operate commercial CDNs, and the ISPs in particular, two fairly large operations are Level 3 and AT&T, who operate CDNs. There's a bunch of other CDNs that are independent, like Akamai. One of the difficulties faced by these CDNs that are based on one or in one ISP is that it's a little harder to sell to a customer if you can't promise, we'll deliver from everywhere. And so there's been talk of federated CDNs, and there are even companies that are going about trying to help independent ISPs federate to form a large CDN. And that hasn't really gotten off the ground, but it's possible that would work. And then I feel like we kind of got into this, things were fairly stable for a while, okay? The industry for maybe the past 5 or 6 years was just kind of moving along. More and more parties were entering into the CDN business. Certain aspects of content delivery became heavily commoditized. So for example, if you look at just delivering static files or video, that business has become very commoditized, very difficult to make any money, because it's relatively easy for any new party to just establish a presence in a bunch of data centers, like 10, put in a lot of servers, and get adequate performance. And so the industry has suffered in some ways the same way the ISPs suffered from kind of commoditization of bandwidth. Now, one thing I want to say, though, is that, and this is one of the 2 or 3 technical points, the one thing that hasn't been commoditized is delivering low latency service, because that is not easy to do. You can deliver with video if you can provide kind of adequate throughput. Latency doesn't matter as much. You may not need to have a lot of points of presence. Low latency, though, is not a commoditized service, and that's where you can charge a premium if you can guarantee lower latency. So all of a sudden, though, I think we've seen some big changes happening just in the last few years. So one of these changes is the emergence of content provider-owned CDNs. So a few of the mega content providers, which include Google, Microsoft, Yahoo, and now Netflix, have gone ahead and said, well, it's worth our while to actually own our own networks and run our own CDNs and go out and peer with the networks where the end users are located. And that's a big change. And what I found really amusing was the announcement from Netflix's CEO that for free, they'll allow you to peer with them so that you can get their content. If you talk to the ISPs, they're like, what do you mean? What do you mean for free? You know, we own all these eyeballs, and somehow, you're kind of muscling us and saying we have to peer with you. But that's been one of the, I think, 10 bold decisions, and one of the new thrusts in the last couple of years. We also have seen these companies like Conviva, and I'm not sure what the preferred term here would be, but these are CDN brokers or meta CDNs, or they're companies that sell client-side software that lets the client choose from among several CDNs that are all offering a service for the same content provider. And this has only further commoditized the CDN business, at least for services where the CDNs are providing something that's interchangeable, like just bit delivery for video. So that's a neat and sort of painful development from the perspective of the CDNs. Another thing that has become important are hybrid CDNs, and here hybrid means a combination of the traditional large-scale centrally managed CDN infrastructure and peer-to-peer technology. And the last time I was here at MSR, I gave a long talk about Akamai's hybrid CDN system, which now has about 35 million to 40 million client-side software installations that are being used to deliver, especially things like large software downloads, which can take place in the background. So that's becoming a bigger part of the business, and it's driven by this incredible pressure to lower costs because of the commoditization of bit delivery. Licensed CDNs, this is a new development. It's an idea of partly trying to head off federated CDNs at the past and having the CDN operator go to the ISPs and say, well, we know you want a piece of this pie. You feel like you should be operating a CDN. How about we provide you with software, but you own the hardware, you deploy it, you have some management capability, but we'll bring the customers and the hardware will all report back to us and you get a piece of the revenue. And so that's coming. There will be large ISPs that are going to be partial operators of global CDNs. Now, I'm almost done with my talk. I wanted to leave this picture in here kind of as a cautionary tale. So I'm not going to overload that. And now we have the wildly futuristic, and I think this is a big question mark, But maybe things are going to radically change in some future internet architecture where we have a more information-centric networking. And I'm not sure if this is the right name either, because there are 3 or 4 other names that have been proposed. But the idea would be that somehow the hardware, the router hardware, or other middle boxes or devices in the network will just sort of, as part of their basic functionality, take over or begin to help with caching. I want to say that one of the big pitfalls that may or may not have been overlooked here, but we can draw a lesson from the upper left-hand corner, is that for commercial content, there's really a requirement that there's high-fidelity reporting back to the content owners. Right? Content owners who have copyrighted materials are not keen on having copies made willy-nilly and served to users without any accounting for it. Even if they don't necessarily care about getting paid for access to it, they want to know who's getting it and what the performance was like. And that problem has to be solved. There has to be some integration, I think, of a reporting mechanism if, for copyrighted materials, we're going to see success with just any router being able to cache content. And so what is going on in this last thing? The whole thing's been turned into a parkway. A park, not a parkway. Sorry, that's more like this. Yeah, back to client server. Yeah. OK, so that's it. Yeah.
You complained about Netflix trying to give away their peering free. Is this a problem that Akamai has patented that notion? Or saying, oh, look, we'll put in servers for free. Just you give us bandwidth for free?
Yeah, I don't oppose the principle. I just don't think you should go out and say it in public and expose it. Right. All right. So what Srini is referring to is that for a very long time, Akamai has tried as hard as possible to get the ISPs or the universities or the big companies to let us put servers in for free and say, look, we're going to give your users better performance, and we're going to reduce the amount of bandwidth you have going to the outside world, which is the same kind of argument that Google or Netflix is making. That's right. And today the ISPs are feeling like, yeah, but in the good old days of television networks, we owned the viewers because we owned the spectrum, and people had to pay us to put anything on our network. And why is it that these content providers aren't doing that? And that's the ISP's attitude. They want to be paid by the content providers.
But the television networks pay. I mean, Comcast pays HBO for content, right? It's not the other way around.
Yeah.
Comparing against television networks, I wouldn't go there.
Depends. I mean, but for commercials, they're charging the commercials.
Let's do this one.
Yeah, sure.
OK, thank you.
Hey, thanks. So I'm Vyas from Stony Brook University, and I'm here today. I'm going to talk about why we should care about middle boxes, some of our very early research in this space, and sort of try and set up like the broader research landscape of interesting problems in this space. To give you some context for this work, the traditional view that we've taken in networking is that the network is dumb. All intelligence is really at the end host. The network is just a bunch of like dumb routers and switches that's just carrying bits through the network. The reality, of course, is like far from it. The reality is like network operators and administrators want a lot of functionality from the network. This is for security, for performance, for policy compliance, and so on. And the way they implement a lot of this functionality is not by changing routers or switches, is by adding a lot of in-network processing through specialized appliances, which we also call middle boxes. And these are things like intrusion detection systems, firewalls, proxies, application gateways, and whatnot. So to understand how sort of pervasive middle boxes are in networks, we did a couple of surveys. On the left is a survey from one large enterprise network. And we did an inventory of like, oh, what kind of devices, network devices are there in that enterprise. So there's like firewalls, intrusion detection systems, media gateways, and other things. The staggering statistic is at the bottom, that the total number of middle boxes in the network is sort of in the same ballpark as the number of routers or traditional IP routers in the network. And if you're just wondering that is this an artifact of this one large network, we also did a much larger survey across several network operators collected from Nanog. And these ranged in like different sizes from like small networks, large networks, and so on. And across the board, what we find is that the number of Middleboxes is typically comparable to the number of routers and switches in all these networks. So in other words, the takeaway here is this Middleboxes are really a very critical piece of the network infrastructure that we as a network community have sort of traditionally ignored. At the same time, talking to the operators who manage these networks, they do perceive a lot of value from the Middleboxes in terms of the performance, security, and policy compliance. But at the same time, our discussions with them reveal like they have like several sources of pain points or frustrations with existing Middlebox deployments. The first pain point for them is that these Middleboxes are really very, very expensive. They incur a lot of high capex from these Middlebox deployments, and adding a lot of these appliances to your network increases the device sprawl and increases network clutter in some sense. And not only that, having a lot of these different kinds of appliances effectively increases your management costs. And in fact, the large enterprise we surveyed almost has like separate management teams for each kind of Middlebox appliance. So they have a separate WAN optimization team, a separate firewall team, a separate intrusion detection team. So it sort of further increases your operating expenses. And finally, they're concerned that today's appliances are inflexible and difficult to extend. Say, for example, we're all worried about mobiles and tablets and so on. And people want to bring these kind of devices into the enterprise. They need like specialized boxes to handle the traffic coming from these consumer devices as well. And the only option for them today is to go and buy more of these boxes. So in some sense, it sends them back on this vicious loop of increasing capital and operating expenses even further. So the goal of this talk and the Middlebox Manifesto is really trying to get the community as a whole to rethink about how we should be building, realizing, and managing such Middlebox functionality. And that's really the goal of the research I've been working on at Stony Brook and at Intel before that. I'll briefly talk about some of the initial ideas we've had in this space, things like building a consolidated Middlebox infrastructure called CoMB, outsourcing Middleboxes to the cloud with a system called Aplomb, thinking about scheduling and fundamental problems in resource management for Middleboxes with a system called DRFQ, and so on. So the first step, what we wanted to understand is what is causing all these pain points in terms of high capex, high opex, and inflexibility. And to revisit this, we actually wanted to understand how exactly does the Middlebox deployment evolve today. So the way it happens is people typically say, oh, I want a firewall, and they go buy a specialized appliance from some vendor, say Cisco or Juniper, to get that firewall functionality. And that particular firewall functionality provides a very, very narrow narrow point solution for a particular kind of functionality. And that firewall also comes with its own custom management interface. So you have this specialized box with its own custom management interface. And as you want to evolve your network to add more of this functionality, your only option is to go buy more of these boxes and buy more of these custom management interfaces. And in essence, this sort of piecemeal or bottom-up approach of incrementally adding specialized boxes increases capital expenses, increases operating expenses, and this way of thinking about the problem is limiting the extensibility and flexibility of these deployments. So what we thought about is like, well, can we take a departure from this paradigm of how Middleboxes are deployed and instead think about what we call a consolidated architecture? And this was work we did at NSDI. And the idea here is to consolidate at two levels. We want to consolidate both the management instead of having separate management interfaces for each kind of Middlebox. We want this unified, you can think of like SDN style controller that's going to provide a unified network-wide view across all Middleboxes. And having this unified controller will actually reduce your operating costs. And at the same time, we also want to consolidate at the platform level. Instead of buying a separate kind of Middlebox appliance for each kind of function, can we say, think of this as like a general purpose hardware platform, x86 or whatever it may be, and try to run these different kinds of Middlebox functions as like apps on this platform. So this gives you sort of extensibility in the sense that you can run any app on any box. You can actually rethink how these Middleboxes are implemented in the software stacks so that it actually makes it even easier to deploy new functionality. So this work showed sort of the promise of taking this consolidated approach, decoupling sort of the hardware-software binding in Middleboxes today, and trying to reduce the capital and operating expenses, and providing extensibility by developing sort of an extensible stack for building Middleboxes. So that's just sort of one sort of point in this space. There's many more fundamental problems with kind of Middleboxes that we're just starting to look at. So one sort of very fundamental networking question is how should we schedule packets when these packets go through these Middleboxes? So we understand fair queuing, we understand queuing and scheduling for packet processing. It turns out Middleboxes are a fundamentally different beast. And the reason is that there's different kinds of resources that sort of come into play when you have this complex packet processing. For example, an IDS might be memory intensive. Something like an IPsec or a VPN gateway might actually be sort of CPU intensive. And when you have different flows from different customers going through this Middlebox, they might actually end up bottlenecking on very different kinds of resources. So in some sense, what we want to do is come up with a scheduling regime or a queuing regime that sort of acts across multiple resources. And in some sense, you can think about this as like sort of generalizing the classic literature on fair queuing to the time and space domain here. And we build on this idea called dominant resource fairness, which provides share guarantees in the sense that two flows sharing the resource are guaranteed to get at least like some fraction of each individual resource. And it's strategy proof in the sense that a flow cannot lie about its resource consumption to get a more than its fair share of the resources available. So our solution is called DRFQ, and it's a sort of nice generalization of the literature in the fairness space and literature in the queuing space to provide these kinds of queuing and isolation guarantees in both space and time. So going further, we actually even thought about an even more radical experiment where you can think of today's Middlebox deployments as this cluttered network on the enterprise side. So one option we thought of is, well, if this is just really some sort of a generic compute service, why not run it in the cloud? So this provides like a new business opportunity for cloud providers, Azure or Amazon, to offer these services to enterprises where these expensive Middlebox functionalities are actually provided as cloud-based services instead of having the enterprise maintain this expensive infrastructure. So there's natural benefits of moving to the cloud. You get these economies of scale, sort of elastic scaling, and so on. It simplifies configuration and deployment at the enterprise side because the enterprise becomes sort of a much cleaner network architecture. And you get like redundant resources, failover, sort of all the goodness of cloud-based deployments. There's obvious challenges here. The challenges are in terms of like, can we provide low performance overhead? Can we provide functional equivalents? Like, can we take a firewall and put it inside the cloud and still get the same sort of functionality in terms of like stateful semantics and whatnot? And at the same time, you want to keep very minimal complexity in the enterprise. If you say, oh, our outsourcing solution needs this very expensive box, you've sort of lost the cost right there. So we've shown some very sort of preliminary results showing the feasibility of outsourcing to the cloud based on measurements and actual sort of prototype with off-the-shelf components that shows the feasibility and promise of this cloud-based Middlebox deployments. So before I conclude, I just wanted to sort of say that we are really just scratching the surface here in terms of interesting problems in the Middlebox space. And just to give you a sense of like what are the interesting problems here, there's problems at the hardware level in terms of like, oh, how do we expose an API for hardware vendors to innovate and expose accelerators to these kind of network applications? There's interesting sort of software engineering questions in terms of how do we build an extensible stack so that you have like an API where application developers can just say, oh, I want to provide a new kind of firewall. There's interesting questions when we say, oh, if you have multiple vendors running on a same platform, how do we provide security and isolation between these different vendors? There's a natural question of, can we tie in to the SDN philosophy? In some sense, this sort of control data decoupling that we've done in Middleboxes can also be seen as some sort of an SDN integration. But there's a natural question of, can we tie into the mainstream SDN world as well? So just wanted to point out there's very interesting problems in this space. We've been looking at some of these, but we're really just scratching the surface, and there's many more interesting problems to look at. So with that, I'll take questions.
Thank you. Questions? I mean, feel free to take questions when we sit down.
Is there a sense for how many of these Middleboxes are actually going to be required in the future? This is an example. Like F5s were not doing what we wanted with load balancers, and we kind of figured out how to not do that.
Yes.
So it kind of is unclear which of these Middleboxes are going to be relics or are they going to persist.
That's actually a great question. So one question that looking at in the sort of tie into SDN world, for example, is that can we provide some of these features with just SDN switches instead of having specialized Middleboxes, right? Like OpenFlow switches gives you like some sort of firewall, some sort of load balancing capabilities. Can we get those functionality without actually buying a separate F5 load balancer, for example? Certainly an interesting question, but things like I imagine things like intrusion detection, security, VPN gateways are unlikely to go away because they're providing a much more deeper semantics that the application developer or the enterprise administrator wants, and that seems harder to provide with sort of generic deployments.
Okay, thank you.
Thanks very much. So I want to mention actually three research thrusts in my group that I think all have some interesting practical takeaways. And the first two are really just very brief teasers. So if you were here for HotNets over the last couple days, my student Ashish talked about our work on building low latency networked systems. And we're really excited about this because as more and more interactive applications move online, latency becomes increasingly critical. And one of the particularly difficult things about achieving low latency is consistency. Unexpected things happen, especially in big complex systems. You have a object that's not in cache or some congestion or a virtualization delay. And so we've been looking at redundancy as a technique to mask exceptional conditions. Now, of course, redundancy has been used in various ways before to achieve low latency. And the basic formula is you have two options. You try both servers, try both paths, use the first one that works. But what we're saying here is that this has been a big missed opportunity, that there's, if you compare the cost of using redundancy to the potential benefit of consistent low latency, there can be a dramatic difference there. And we should be using much more redundancy than we are today. And we can get significant benefits in systems like DNS or Memcached. So that's been some interesting work, and also even on the theory side, characterizing when this is a good idea. A second research thrust is in data center network topology. So if you look at what data centers are, how they're structured today, traditionally it's like a tree. Tree-like network. If you're in a high bandwidth scenario, then you're going to use something like a fat tree. But there's no reason it has to be like that. And since it's October 31st, we might as well pick something rather scary. How about a random graph among your top-of-rack switches? So this is something that we've been working on. And it turns out that there are two good reasons why you actually might want to use a random graph in your data center. One of those is that they are highly flexible, easy to incrementally expand, easy to incorporate heterogeneous components. But then you might think, well, OK, are you going to give something up by using this messy topology? Is it going to be harder to get high throughput in your network? But it turns out for throughput, actually the opposite is true. And random graphs are, we can show, very close to optimal topologies for throughput. In fact, with the same equipment as a VL2 topology, we could get roughly 40% more servers with the same equipment at full throughput. And this is at the scale of several thousand servers. The benefits are a little smaller for smaller sizes, bigger for bigger sizes. Now, there's certainly practical challenges here, but they appear to be solvable. So this has been an interesting direction. OK. So now the third thrust that I want to talk about is data plane verification. And I'll spend a bit more time on this, although not too much, because I have to catch a flight. So I won't run on too long, I promise. So I probably don't need to spend time convincing you that networks are complicated. Production networks are complicated. Managing them is a difficult task. There are interactions between protocols, security policies, and things go wrong, even in well-managed networks. And unfortunately, there are few good tools to help network operators formally understand what is actually happening in the network, what's going on. Taking a real example from the UIUC network, we had a dorm and intrusion detection and prevention device in front of it, and then various other parts of the network. This box was getting overloaded. Maybe Vyas could help with that, but the operators didn't have that, so they put in a bypass router so that some traffic would go through the IDP and some that didn't need it wouldn't. And of course, this involves a change to several configurations. And did it work? How do you know? How can you be sure that it worked? It affects performance. It affects security, right? And in this case, actually, it didn't. It introduced some bugs. How could you check that? Well, there has actually been some past work on verifying network configurations. And this is useful for several reasons. But we think it's got this challenge fundamentally that it's trying to predict a lot of what happens in the network. The approach that we've been taking instead is to diagnose problems as close as possible to the actual behavior of the network. We want to see what's really going on and understand whether it's correct or not. So we call this data plane verification, grabbing a snapshot of the data plane state and seeing what's happening. And we've been building a couple systems in my group and in collaboration with Professor Matt Caesar also. The first was Anteater and SIGCOMM a little over a year ago that did offline verification of the data plane. And Veriflow is our second generation system that verifies networks in real time. So what does this system look like when you're verifying the data plane? Well, first, you need some input. You need to know what the network looks like. This is a snapshot of the data plane state, the topology, forwarding tables, ACL rules, etc. And then from the operator, what you want is some invariance. What should the network be doing? So for example, there should be no loops in the network. Or packets from this VLAN should not leak onto this other VLAN. Or packets that reach this server should not have been able to come in here without going through a firewall. That kind of question. And now we can take this in a network verification layer, build a model of what's actually happening in the network, and check those invariants against it, and then provide a report to the operator. So we built this system with our first generation system, Anteater, and used it to check the UIUC network. And in fact, there were a bunch of different bugs that turned up. For example, you can do consistency checking between two routers that should be behaving the same way, but in some cases had some different security policies in how they were exposing management interfaces. And another example was forwarding loops. Going back to this example I had a bit earlier, it turned out that the changes to the configuration.
Was there any harm being caused? How did he pick it up? You just sort of just doing it and then you picked it up?
Was there harm being caused by these forwarding loops?
No, but the previous, as you were giving the example of your UIUC.
Right. Right.
You said we found routers were supposed to do the same thing, but not doing the same thing, right? Which is what you said?
Yeah. So OK. So in that consistency check example, that was a management interface that was supposed to be private, but on a certain network, it was exposed. So you could connect to a router.
What triggered you to look at it?
Oh, what triggered us to look at it? OK. So I mean, this gets to a question of how are you going to actually conveniently express what should be happening, because that's not easy, actually. And we think there are several things you can do. Like, if there's a loop in the network, that's clearly bad, right? But another convenient thing, and this is why we picked this, is, well, I know that this piece should be doing the same thing as this other piece, consistency checking. So these were replicated routers that should have been doing the same thing. Right? And so now we don't need to explicitly say exactly what should be happening, but we can compare. And another thing for the future that might be interesting is bringing in control plane verification work. Compare the control plane to the data plane. Do they actually match? Right? So there might be some interesting things that you can do there to do more convenient checking without involving much of the operator's time to say in detail exactly what should be happening.
So you're doing it proactively rather than doing anything. So it's verification and not diagnosis per se. Right?
It's not tracking down the root cause, if that's what you mean. Right. I mean, but it's helping. It helps significantly. So for example, in this case, once we pointed out, oh, there's this loop that could get triggered, then it was easy for the operator to verify that and go into the configuration files and fix it. Now that was with our first generation tool, Anteater, which did offline verification. And with Veriflow, we took a more ambitious question. And that was, is it possible to actually check network-wide invariance in real time as the network evolves? And if you can do this, then you have something even more exciting. Then you can provide real-time alerts. You may be even able to block bad changes to the network before they even enter. Right? So there are several challenges with this. First, you need to know in real time what does your data plane look like. Okay? And for this, we're operating in an SDN paradigm. So SDN gives us a logically centralized controller with software abstractions on top. And we're basically interposing Veriflow right there at the controller so that we can see a stream of updates going by. And each change to the network we verify before it gets sent out. Now, if you want to do that, you have to do that verification extremely quickly. And as a rule of thumb, we're taking 1 millisecond as a target. I don't really have time to go into detail on the algorithms here, but here's just a little bit of the flavor of how we do it. We get a stream of updates in, and the first thing we do is slice the network into equivalence classes, sets of packets that have the same forwarding behavior. And then we can narrow down basically a slice of the network that a particular change affects. Once we have that, we can build a representation of what's happening in those slices, which we call forwarding graphs, and then check queries within those slices. So if we find now that some update satisfies all the invariants that are essential, we can send that out to the network. And if it's bad, we can either block it completely or maybe just trigger a real-time alert. That's a very high-level overview of what happens on the inside. And it works fairly quickly. So this is a emulation of about a 170-node network with a realistic trace of updates. And the nice thing is that 97% of updates were verified within 1 millisecond. And another nice thing here is the phase that actually checks queries is pretty fast. So we can do more complex work, maybe check more invariants, and still are able to operate in real time. Let me just mention a little bit of related work, because there is some, including some algorithms for static reachability in IP networks that are of this flavor. There's a config checker work from Al-Shair et al., which is of the data plane verification flavor. And as a system, Anteater's contribution over this was the first system to actually demonstrate the usefulness of this in the real world, checking a real world network. Subsequent to Anteater, there's a very cool project out of Stanford called header space analysis, which is essentially going after the same goals as Anteater, but with a different internal algorithm. But is also not in real time, at least not in that version of the paper. OK, so just to conclude now, I want to mention 2 takeaway points here. First, data plane verification is valuable. You can have a network-wide understanding of what's actually happening in your network, and you can really find real-world bugs. More than that, real-time verification is, in fact, feasible. And this opens up, I think, an exciting direction of providing a real-time understanding of what's happening in your network that you can build higher-level functionality on top of for management, for monitoring, and for security. And there's a number of interesting directions there. All right, that's it. Thanks.
Any questions? You can take
questions.
Some questions while we're changing.
So regarding Veriflow, then, if we're using an SDN-based approach anyway, why do you have to verify the rules that you have just generated?
Why do you have to verify the rules you've generated?
Yes.
Well, they might be buggy.
Yeah, then you should fix the bug in the first place.
Yes, we should not have any bugs in our systems. I agree. No, I mean, I think it's. I think you're right that in general there's another big opportunity with SDN, which is now we can have much better programming models so that we don't have those bugs in the first place. On the other hand, I don't think we're ever going to be able to completely get rid of bugs. And not only does SDN make certain things easier, it also gives the opportunity for writing much more complex software, for using software written by multiple parties or even multiple controllers. So you might want to have this certainty or more certainty that things are going on at a low layer. And I think that can tie in with the programming model and give some feedback there.
We'll take, I'm sorry, we're running out of time.
Okay. And I have to catch a flight. So.
Thanks.
Thank you.